Hello, today I'm going to discuss on the topic radioactive decay. However, let me provide the premise by discussing first on the nuclear stability. Okay, nuclear stability is determined by the difference between Coulombic repulsion and short-range attraction. Why? Recall Coulomb's law. The French physicist Charles Augustin de Coulomb stated that like charges repel and unlike charges attract one another. It follows, therefore, that protons will repel strongly from each other, especially since they lie close to each other. But in addition to this repulsion, there are also short-range attractions between proton and proton, proton and neutron, and neutron and neutron. If the force of repulsion is higher than the force of attraction, the nucleus will disintegrate, thereby emitting particles or radiation. If the attractive forces are higher, then the nucleus is stable. The principal factor that determines whether a nucleus is stable is the neutron to proton ratio, N over P. For stable atoms of elements having low atomic number, the N over P value is close to 1, increasing with increased atomic number. We can predict this nuclear stability through the following rules. Number 1. Nuclei that contain 2, 8, 20, 50, 82, or 126 protons or neutrons are extra stable. We call these numbers as magic numbers. Number 2, nuclei with even numbers of both protons and neutrons are more stable than nuclei with odd numbers. Notice that there are 164 stable isotopes for even to even or neutron to proton ratio much higher than 53, 50, and 4 for other combinations. I have already said in number 3 in another video, isotopes of the elements with atomic numbers higher than 83 are radioactive. And number 4, an exception to the third rule are the isotopes of tectenium Tc and promethium Pn. These elements, despite having atomic numbers of 43 and 61 respectively, lower than 83, are radioactive. We will understand nuclear stability better if we look at the neutron-proton plot. This is the plot of the number of neutrons, the y-axis, versus the number of protons, x-axis, on various isotopes. Isotopes are represented by dots. This straight line represents the point where the x, number of protons, and y, number of neutrons, intersect, resulting in a neutron to proton ratio equal to 1. The stable nuclei are in the belt of stability. Those that are outside the belt are mostly radioactive nuclei. If the intersection of X and Y lies above the stability belt, it means that the nuclei have higher neutron to proton ratio than those within the belt for the same number of protons. Below the belt are for lower N over P ratio. To lower the entropy ratio and move towards the belt of stability, the nuclei undergoes a series of processes. When unstable nuclei spontaneously changes into another, we refer to it as radioactive decay. For example, we have a parent nucleus, uranium-238. When it decays, a daughter nuclei is formed, that is thorium-234. The daughter nuclei can either be stable or unstable. As the decay progresses, the daughter nuclide lies closer and closer to the band of stability. Hence, we can use the neutron-proton plot to determine the type of decay going on in a reaction. What are these types of radioactive decay? For this video, we will only discuss the 5 common types of radioactive decay. The first type is alpha decay, which we had already discussed in another video. In this decay, the general equation is x superscript a subscript z into x prime superscript a minus 4 subscript z minus 2 plus alpha particle superscript 4 subscript 2. That is, the daughter of a parent isotope x prime will have an atomic number that is 2 less than the parent, or z minus 2, and 4 less atomic mass unit than the parent, or a minus 4. Thus, for example, polonium-212 with atomic number 84 decays to its daughter lead-208, losing atomic number to 82 and emitting the alpha particle helium-4 with atomic number of 2. Alpha particles are large and are therefore unable to penetrate very far into the air or the surface of a material. Hence, they deposit their energy in a small area near the emission. Most alpha decay processes happen with atoms having mass numbers greater than 200 atomic mass unit. It cannot penetrate the skin. The next is beta emission. There are two types of beta particles. The most common beta particle is a negative beta particle. Negative in the sense that the neutron in the nucleus of the parent isotope decays to form a proton so that the atomic number becomes Z plus 1 for the daughter X prime. There is also the emission of a high-energy electron negative beta along with the extremely small particle antineutrino, nu e, and an antineutrino does not interact with most matter and oftentimes is just hidden in the equation. Since the neutron and the proton are about the same mass, the mass A of the daughter isotope X prime does not change. In our example, the parent K40 with atomic number of 19 decays to form a daughter Ca also of atomic mass of 40 but with atomic number increased by 1, hence 20. In the periodic table, the daughter element Ca will change position by 1, placing it to the right of the parent element K. Take note also that these changes result in the decrease in the N over P ratio, thus moving the daughter particle closer to the belt of stability. Notice also that the other product of the reaction seen in the equations, the beta particle, which has a negative subscript 1 and 0 superscript. The third type of radioactive decay is positive beta decay or positron decay. This decay happens with nuclides whose N to P ratio is low, so it lies below the band of stability. During the process, a proton in the nucleus of the parent decays to form a neutron and emits a beta plus particle, a positron, together with another extremely small particle, the antineutrino, nu A, as I said a while ago, usually hidden in the equation. The decay of the parent isotope X produces a daughter isotope with the same mass, since while there is an increase by 1 of the neutron, there is a corresponding decrease by 1 in the protons. Of course, the decay also increases the N to P ratio, so the daughter nuclide created gets more closer to the band of stability. Our example here is the parent isotope potassium-38 with an atomic number of 19. It undergoes beta decay or positron, thereby creating the daughter isotope argon-38. Notice the change in atomic number from 19 to 18, meaning from 19 protons to 18 protons, but with no change in atomic mass 38. If you check the periodic table, because of the decrease in proton, there is a one-place change to the left of the potassium in the periodic table. And wondering why argon is on the last column to the right? Well, since there is no other column to the left of K in the periodic table, the logical position is to go around to the last column. Now we go to the fourth type of decay, the electron capture. For nuclides below the region of stability, they have low numbers of neutron. So there are two possible decay that will happen. One is the positron decay or beta plus decay, which I discussed a while ago, and the other is electron capture. Notice that both processes increase the neutrons by 1 and correspondingly decrease in the number of protons or atomic number by 1. Hence, also result in the parent and daughter isotopes with the same number of protons or atomic number, and similarly changing the position of the daughter isotope by 1 column to the left of the parent, the periodic table. Again, the decay also increases the N to P ratio, placing the daughter nuclide closer to the band of stability. Our example here is the parent isotope potassium-40, the same element as the previous example but different isotope. The difference in that decay process is that in the beta decay, proton is converted to neutron with the emission of the positron, while in the other decay, an electron in the inner shell, the one nearest to the nucleus of course, of the parent isotope is captured by a proton, converting it into a neutron. In other words, the neutron in the beta decay emanates from the nucleus, while the neutron in the electron capture emanates from the electron cloud, But what happens to the inner shell that lost the electron? Well, it leaves a vacancy that will be filled by one of the electrons in the outer shell, and when it happens, it will then emit energy. And wondering which of these two decays is going to occur? Well, primarily, the decay process which requires a smaller activation energy for a specific parent isotope is more likely to occur. Finally, the gamma emission. In this decay, the number of protons and neutrons in the nucleus does not change, so the parent and daughter isotopes are the same chemical element with the same mass number. There is no particle emission in the gamma emission. Rather, you have an excited nucleus, usually represented by the asterisk that directly emits the gamma ray as it transitions from a higher energy state to a lower energy state. This is what happens in the nuclear reaction cobalt-60 asterisk into cobalt-60 plus gamma. Also, a gamma emission can happen when an excited nucleus emits the gamma ray immediately following one of the previous four types of nuclear decay or from the annihilation event of a positron interacting with an electron. Thus, we have the reaction uranium-238 into helium-4 plus thorium-234 plus gamma ray. FYI. Gamma rays are a very high energetic form of electromagnetic radiation. They do not carry overall electrical charge, but they can dislodge electrons out of the atom and make it electrically charged. This is why gamma rays are referred to as ionizing radiation. Gamma rays can penetrate deep into the skin. Okay, one down and more to go. Open your heart, guys, and enjoy the journey. But before you do that, will you please hit subscribe and like for this video? Thank you so much.